Hi, welcome to a new section of this course, Queues. In this section we'll look at functional persistent FIFO queues. We'll also look at priority queues, which are implemented using heaps. We'll familiarise ourselves with the core data structure and how it's implemented in the imperative world. We'll soon see why we need another data structure to realise functional heaps and introduce leftist trees. We'll develop a functional priority queue using leftist trees. Now we move on to the first video of this section, FIFO Queues. In this video we'll learn to remove the tail node, go for a doubly linked list, and pop out another element. A queue is another fundamental data structure. It's heavily used in many contexts. Queuing up tasks is a very common requirement. For example, if we look at the producer-consumer pattern, we see that both the producers and consumers communicate using a queue. FIFO queues are used for implementing the first-come, first-served strategy. For example, let's consider a queue for booking movie tickets. The person who comes first and joins the queue gets serviced before the person after him, who joined the queue a bit later. This enforces an order, which is also known as first-come, first-served, or FIFO. According to this, the person who comes earlier is serviced first and moves out of the queue. A new element queues up at the head and is removed or serviced at the tail, as shown in this figure. In the imperative world, it's pretty easy to see how we would implement a FIFO queue. We could maintain the FIFO queue as a singly linked list with two pointers, one at the head and another at the tail. We'll remove the tail node, that is, pop the element off the queue as we need to traverse the entire list to reach the last element. We'll insert a new element at the head node, or in other words, push the element to the queue. These would be simple list operations, mutating the list to reflect the changes. To improve the performance of the pop operation, we could instead go for a doubly linked list. This would help us pop the last element easily, thereby making it a big O of 1 operation. In this case, note the space trade-off, we get a faster removal operation. Every node needs to maintain a pointer to the previous node. We know by now that all this mutating won't work when we deal with persistent data structures, which are also known as versioned data structures. How can we implement these queues so that when an element is enqueued or dequeued, the earlier version of the data structure would be preserved? The design is beautiful. It involves two lists. This diagram shows two lists, namely in and out. The out list holds the elements that will be popped out. We just remove the head element and return it. The in list is where new elements are inserted, that is, prepended. As we've already seen, both list prepend and head removal are big O of 1. For example, given the preceding diagram, when we remove the element 9, we get another version of the persistent queue, V1. Have a look at this figure, which shows the persistence in action. Note the indices for both the versions. Now let's pop out another element, 7. This will make the out list empty. Of course, this will create another version of the out list, V2. This will be empty, as shown in this figure. Now we have a situation where the in list is non-empty and the out list is empty. In this case, we reverse the in list and then swap it with the out list. This is shown in the previous diagram. This operation is called a pivot step, and its cost is big O of n. There is another way to look at it. We can either have both the lists empty, meaning the queue is empty, or just the in list. We'll never come across a situation where the out list will be empty and in list non-empty. This is an invariant. That is, a condition that always holds. The condition could be violated for a moment, leaving the invariant broken. In such cases, we do the needful. Swap in .reverse function with out and restore the invariant. In this video, we explored about FIFO queues.